Okay, so let us continue our discussion on algorithms for relational algebra operators. Join is a very important operation, as we have seen earlier in query formulation and all that. So, in the last lecture I was talking to you about algorithm in a slightly hurried manner. So, I thought I would start off with join processing and then let people synchronize with this. Earlier to this we just discussed external sorting and various issues in doing other operators like select project. Okay. So, let us focus on join today. Join, we will consider two-way join, where we have two files of records and then we are given a join condition and we need to join the records and produce the output. Notice the minimum that you can, the minimum time that you need in order to produce join is the sum of the total of blocks in file 1 and file 2. You have to look at all the if you don't have indexes. If you do have indexes, then we are slightly better off, but if you do not have indexes on either of the file, then the lower bound on the amount of time that you need to do for processing join is that you basically have to look at all the data records. Now, okay, so so we will discuss a few algorithms for doing join processing, and then so at a particular, for a particular join you have to choose one of these operations, choose one of these algorithms and then apply that algorithm. So, the choice of the algorithm depends on the sizes of the files that are involved in the join and what is the primary organization of those files that are there, and what are the available indices on the join attributes. The indices have to be on the join attributes. So, are there indices on join attributes, and we will introduce an idea called selectivity of the join condition, and even this has to be taken into consideration before you choose the appropriate algorithm for join processing. So, we will basically discuss 2-3 of these join algorithms, and then the choice of course depends on many factors. The actual join is being used for a specific relational algebra operation. Okay, so we briefly talked about nested loop join yesterday. So, let me repeat this idea. This is a brute force join. It's a brute force join. We have two data files R and S, R with B1 blocks and S with B2 blocks, and we always assume that there is a certain amount of memory that is available to us, RAM space, and we will take it as M blocks of RAM space. Okay. So, we have M blocks of RAM space, and the algorithm is very simple. It is a double loop. So, for each record X, it is a nested loop. So that is why this is also called nested loop join, block nested loop join. So, for each record X in R, do this thing which is again a loop. For each record Y in S, check if Y joins with the X, and if so, produce the join result. What do you mean by joins with? Basically check the join condition, whatever is there. So, in most of the discussion here, we will simply assume that we are doing an equijoin, but the issues are similar for if we have other conditions. Okay. So, as far as the buffer usage is concerned, we have M blocks. So, one of these blocks, once the space of about one block we will reserve for storing the result of the query, result of the join, and for the inner file, which is S, we will use M minus 2, we will use one block for the inner file and M minus 2 for the outer file, n-2 for the outer file. And the basic idea here is that since we are using external files, we will read as large a chunk of the outer file as possible into the main memory and then make use of it fully before you move on to the next chunk of the outer file. So, that is the basic idea. So, for each set of m-2 blocks of R that are read in from the disk file of R, disk file corresponding to R, we will do this. So, we have reserved one block space for S, right. So, read the records of S, the inner file, into that one block by block you read the records of S. Okay. So, when you read it in, then you have access to a bunch of records, then you can find out whether they join with any of these records of R, and then you can produce a result. Okay. So, once you read a block, compute the join and write the result. 2, we have kept one block for writing the result, the join result, right. So, we will write records into that block, and as soon as that block is full, we will write it to the disk. It is a buffer space. So, we fill it and then keep writing it to the disk. Okay. So, this is what we will do. So, essentially instead of for each record X in R, we are now taking a chunk of records R and then reading the entire S file. Okay. And then producing the join results. So, that chunk is m-2 blocks. Okay. So, as far as the time taken is concerned, you can now see that if R has B1 blocks, S has B2 blocks, and buffer has n blocks, then the number of times that inner file has to be read is basically B1 divided by m-2, where B1 is the number of blocks in the outer file, the R. So, overall the complexity in terms of block accesses will be that the entire B1 blocks have to be read. So, B1 plus this many number of times you have to read the inner file. So, B1 divided by m-2 seal times B2. So, that is the overall complexity. You can see that there is a quadratic term that is coming up here. It is a multiplication of the two sizes of the files. So, this algorithm is truly a quadratic algorithm because it has two loops, right. You can see that the quadratic term is coming. Okay. Now, you can choose the file S to be the outer file and R to be the inner file. So, by symmetry you will get this other expression, and so of course, one small point here is that this factor is roughly the same in both. So, you can choose so among the two choices you can choose the file which has smaller number of blocks on the outer loop, so that this will be little small compared to the other. So, here we have B1 has 5600 blocks and B2 has 120 blocks, and the buffer has some 52 blocks. Then you can see that if you substitute into these expressions, you will get either this many number of disk accesses, or if you take the S in the outer loop, then 120 plus 120 by 50 times 5600, so that many number of disk operations. You can verify this later. but there will be a slight advantage. So, it's 190 seconds versus 170 seconds. Okay. So, this is the situation when we really do not have any support of indices for the files. Now, let us look at a situation where we have an index on one of these files. So, this is called single loop join or index loop join algorithm. So, again we have two data files, let us say R has B1 blocks and S has B2 blocks, and we need to compute the equijoin with R dot A equals S dot B equijoin. So, let us now assume that we have an index on S. So, the index of course has to be on this attribute B, some arbitrary attribute will not help us. So, on this join attribute B, let us say we have an index on S. What does it mean? It means that given a value for the attribute B, I will be able to get hold of all the records that have that particular value in the S file in some few number of block accesses, depending on the indexing technique that we have used. Okay. So, this is much better because we really can avoid a loop over this S. Okay. So, what is the algorithm? So, the algorithm is for each record X of R that we read in do this. What is it? Use the index on B for the record for the other file S, get all the matching records having B equals X dot A. So, X dot A you can pick up from the record that you have read in. So, that is the value that matches the produces So, if a record in S has exactly this value, then it will produce a result for the equijoin. So, now you can use this value, consult the index, get hold of all the records that have the specific value in the S file and then produce the join. So, this way we are able to avoid a looping over S. So, we will do a single loop which is on R. For each record X of R, we do this. So, the time taken obviously time taken is easy to find out here. B1 is the number of block accesses that we have to do in order to read all records of R, we have to read in. So, in each record when we read that, we have to do number of block accesses for those matching records, we have to find matching records. Okay. So, the block accesses using the index we will at least be making this many, we will be making at least this many number of block accesses. Okay. Now, essentially having a index will greatly help us in reducing the time from quadratic to some kind of a linear. Now, there is one other important issue that comes up, which is called join selection factor. What is the fraction of records in a file that join with records in the other file, okay, for this specific given condition. So, let us illustrate it with an example. So, consider this join professor relation joined with department relation with the join condition employee ID equals HOD. See, oftentimes we may have to find out details about the HOD of the department. So, the details of the employee are there in the professor table. So, we want to do an equijoin with professor employee ID equals HOD as the join condition. so that we can now pick up for each department, we can pick up details about the head of the department from this join, result of the join. Now you can see that from the domain we have we have some information about this equi-join. It is that every department has to have a HOD and that has to be a professor, and every professor need not be a HOD of some department. And so if you have some 500 number of professors and only 25 number of departments, you know that for only 5% of the professor records will actually have a matching department record, right. Only 5% of these professors are actually HODs, rest of the 95% people are not HODs. So if you try to join an employee ID with a HOD ID here, 95% of the time it fails. Whereas 100% of the professor departments will join with professor rows, because each department has to have a HOD, has to have a professor as a HOD. So this is purely actually domain knowledge, right, the relationship between this professor and department. So these are called the joint selection factors, the joint selection factors. If you know them, then it is really helpful, because it is going to impact the performance of the single loop join. Let us say the indexes are available on both files. Let us say indexes are available on professor file, on employee ID, and department file on HOD. Let us assume that for a moment. Then it is an obvious choice that we should actually loop over the records of the file that has a high join selection factor. Join selection factor. So this particular file has high join selection factor, because 100% of these records will join with other file, whereas this one has low join selection factor, because only 95% of these things will join. So let me illustrate that here. So the join selection factor does impact the performance of this single loop join. So loop over professor records and probe the department. We call probing the department, because you will get the value for employee ID from professor record, and then you use an index on HOD to probe the appropriate department. Okay. So that is option 1, and option 2 is loop over department records and probe the professor for using the index on employee ID. So in the option 2 you can see that whenever you do a probe, you will succeed, 100% success is there. Whereas here whenever you do a probe, only 95% of the only 5% of the time you will find the corresponding HOD, corresponding department. So 95% of the probes do not give a match, and so it is a lot of wasted usage of the index, wasted usage of the index. So in order to figure out this, it will have to do some disk accesses, right, because this index is a disk data structure, it is lying in the on the disk, so it will spend some disk access. It is a wasted effort. So this joint selection factor thus will influence as to what is the correct way of doing the join, which one is to be used as a in the outer loop, and whose index has to be used. Of course, this is assuming that indexes are available on both files. Okay. And so what happens is that for the popular join predicates that the system is encountering, it will maintain these join selection factors. Over a period of time, it will accumulate knowledge about join selection factors and store them in the catalog, so that for future uses of these predicates, join predicates, it will make use of that and then make appropriate choices. Okay. Now let us see how we can make use of the good old idea of hashing, we have seen hashing can be used for index building in the last few lectures earlier. So now it turns out that the beautiful idea of hashing can also be used to construct a good algorithm for joining. Okay. So let us see how hash joins work. There are a couple of variations for this hash join, let me try to cover them now. Essentially using the idea of hashing. So here is what is the hash join algorithm is. Again let us consider a two-way equi-join or joins with S with join condition R dot A equals S dot B. Now let us make we will relax this assumption a little later, but let us now make an assumption saying that the size of the file S is such that it fits into the memory. We have enough space in the memory or the file is small that fits into the memory. Let us make this assumption for the moment. So if you do now what you do is read the records of S, use a hash function h, and then hash these records of S on the attribute B, on the attribute values B will be there. So use them and supply them to the hashing function that will give you a bucket number and put them into m number of buckets, whatever be the number of buckets that hash function requires. So remember that we made an assumption that S fits into the memory. So all these m buckets are actually sitting in the RAM now, they are in the memory for us. So the entire file is in memory now, but it is sitting in such a way that the records are distributed hopefully evenly among all the m buckets. Okay, that depends on the hash function, right. So we will not go, you have studied hash functions earlier in data structures course, so we will not go deep into that. But basically choose the appropriate hash function, hash the records of S using the B values and distribute them over these m buckets. So this is called the partitioning of S. We basically partition S, records of S into buckets. Now in order to produce the join, what we do is now start reading the records of R. R does not fit into the memory, but you can read block by block. You can read block by block the records of R and then use this A values, and then use the same hash function and hash these records onto the same buckets, not for the purpose of storing, but for the purpose of finding out as to which bucket it is going, right. Suppose you read in a record R and it goes to the second bucket, then you know that is the only place where matching records can be found, because the value of if the value of R and the value of S are indeed same, then the hash will produce the same bucket number. The hash function will produce the same bucket number, right, applied to A as well as when applied to A or when applied to B, the hash function will produce the same bucket number. Okay. So you have already done the hashing on B values, so the records are all there in the buckets. Now use the hash the records of R, So if using the same hash function, right, use the same hash function and use the same m buckets. So then you will find that the matching pair of records will hash to the same bucket. Okay. So you read in a record of R, you hash it and then you go to the bucket 10, then in that bucket you can search for matching records. You will not find these matching records anywhere else in the file, you will only find there, because that is the property of the hash function. and that is a small space. So, you can search there and then figure out all this. Okay. So, is this idea clear? It is a very interesting nice idea using which we can make use of hash functions in order to compute joins. But the only problem now is that we have assumed that S fits into the memory. Okay. So this, I suppose this is clear, right. So, if one of them fits into the memory, then we can use this hash idea in order to produce the join results. Are there any questions on that? Can I proceed? Okay. Okay. So, now let us look at a variation of this algorithm called partition hash join. Here we will relax this assumption that S fits into the memory, we will not assume that. So, neither R nor S fits into the memory. So, they are actually two large files and we are supposed to compute a equijoin on them. So, a two-way equijoin R join R dot A equals S dot B S. This is what we are supposed to do. R is big, S is big, both of them do not fit into the memory. Now, we do what is this, we will do it in two phases. We will have a partition phase and a probe phase. In a partition phase, what we will do is choose a hash function h appropriately and then hash the records of R into some m number of buckets using these A values. Okay. Now, the file R is big. So, you can use memory buffers for each of these buckets, and then as soon as those buckets are getting filled or something like that, you may have to write them to the disk. Okay. So, write all these R1, R2, Rm, all of them back as files. Okay. Is that clear? So, we basically what we did is to use a hash function on values on the A values and partition the records of R into M files into. So, let us assume that this the hash function produces M buckets. So, we are now going to get M sub files. The only property that these files have is that all of those that have all those records that have a particular hash value will go into one particular file. Okay. I can choose this M to be large enough. Now, do the same thing for records of S. Use the same thing for the records of S. So, we have written all these files back onto the disk. So, we have basically replaced R by R1, R2, Rm. Now, do the same thing for S, S1, S2, Sm. Now, of course, use the same hash function, but then use B values. And the idea here is that choose the hash function such that the distribution is uniform and at least one of Ri and Si fit into the memory. Okay. At least one of Ri and Si fit into the memory. Now, how do we ensure this? This we can ensure by, usually we use hash functions of having mod m kind of things, right. So, you can increase that value m and then that will produce a large number of buckets, and then if it produces large number of buckets and then the records are uniformly distributed all these buckets, then the bucket size will be small. So, you can choose the number of buckets appropriately so that the file fits into the memory. Individual files fit into the memory, one of them at least, say Ri or Si. So, this will be the goal of choosing the hash function. So, now you would have got an idea as to why we are doing all this. Now, in order to do actual a join between R and S, all that we have to do now is to only do join of Ri with Si. So, to compute join result, all that we have to do is to simply compute a Ri and join Si. Okay? Do you get this idea? This is a very important idea. The records of Ri cannot join with anything other than records of Si. So, you can give a simple proof by contradiction for that. In case it is so, then you know the matching record, you know, yeah, let us assume that you taken a record in Ri, okay. That means the hash function sent it to some bucket I, okay. So, if there is a matching record for this, how can the same hash function send that matching value to something other than I in the other case? It has to send it only to I, to the bucket I. So, that is why basically join of R and S has now got reduced to joining of Ri and Si for all values of I corresponding R1 join R2, R1 join S1, R2 join S2, etc. If you finish all of them, then you are done. That is a good idea. Now we are back to the sub problem. So now we can use the hash join where we have assumed that one of them fits into the memory, right. So in the, we call this a probe phase. So in the probe phase, basically what we do is join Ri with Si for all I. Okay. We have produced equal number of pairs Ri Si. Okay. So there are again, so we try to fit in, we try to choose this hash function such that either Ri or Si fits into the memory, okay, but we might sometimes fail also. So there are two cases that might arise. So if one of Ri and Si fit into the memory, then in order to produce this join, we can basically make use of the hash join that we discussed just now. So hash the smaller of the two into the main memory using a, obviously you should now use a different hash function. You should now choose a different hash function, you should not choose the same hash function as we have done for partitioning case. Because we are now two separate files, we are now hashing them, we have to partition them now. So you have to use a different hash function, say H2, and then distribute the records of one of the smaller file into buckets, and then read the other file, probe and produce the results, just like we did for hash join. And the overall cost will be 3 times the total number of blocks that are there in R and S. Can you tell me why? Yeah, it should be obvious, no? I mean, because we did a partitioning phase. So for partitioning phase, we have to read the whole of R, whole of S, and then write them back. That is why it gives 2 block accesses, R plus S, again R plus S for writing back, read and write. And then for this hash join, again you have to read S and then apply a different hash function, and then read all of R to start probing the hash function. So 3 times, but it is linear. Of course, you also have to take into consideration that the result, you start producing result records, right. So, they are there in a buffer, so you have to keep on writing them back to result, so that also will cause some block accesses. So, plus the size of the records, that will be the number of block accesses you can do. So, partition hash join is not quadratic, so it is at least linear, so it is useful in practice. So, the other case here is neither okay, both of them do not fit into the memory, but then we have to basically fall back onto nested loop joins and then the overall complexity will be 2 times R plus S plus the cost of the nested loop join on that particular Ri and Si. Of course, these cases might differ from each I actually, so we should probably put this cost separately. Okay, so these are the ideas using hashing that we can actually produce nice algorithms for giving join results. Okay, so now we can also use the idea of merging, the idea of merge sort merging in order to produce a join result actually. Okay. So, this is applicable in some selected cases. So, let us see what is that. So, let us again consider a two-way join like this, or join with R dot equals S dot B on S, and let us say R is sorted on A and S is sorted on B. So, if you have sequential or sorted files on these respective attributes, then we are very lucky. Well, this is not also uncommon also. See, sequential or sorted file organization is a common file organization, and let us say you have doing a join on the primary index of one file and the primary index of other file, and both of them happen to be sorted files. Then we can exploit this algorithm. So, if R is sorted on A and S is sorted on B, then what we can essentially do is to actually make use of the idea of merging. So, while merging, the idea is to actually produce them one after the other if they have equal values, but here what we will do is, instead of doing that, we will simply say that if these have equal values, then they are going to produce a join result. So, we will use the process of merging, but we will produce a different result, we will produce join result. Okay. So, but the advantage situation here is that if you are considering a particular value x here in the sorted file, and approximately all the matching files will be at the same place in the other file, because that is also sorted. So, you do not have to go all over the file in order to figure out the matching results. So, this is called a merge join, and it is really very efficient because it is also linear. In the number of block accesses that you will do on R will be proportional to its size, and then the same with the other file. So, you basically do a linear, you pay a linear cost for this merge join. So, merge join can be also made use of for producing join results. Now, in a situation where you do have a data file that is, one of them is sorted, the other one is not actually sorted, then maybe sorting the other file temporarily on this join attribute and then using a merge might actually be a better way of producing a join result, join output. Okay. So, you have to weigh the costs there. So, sorting the other and then using the merging might be a cost effective technique to produce the join result if one of them is sorted in the join attribute. Of course, you can make use of this sort merge join on some two data files no, by first joining sorting R on A and sorting S on B and then using a badge. But that is likely to be costly because as we have seen sorting itself is a costly operation. Okay. So you will have to, so these are the various options that we have while producing joins. So if nothing works, worst case is the nested loop join. If an index exists on one of them, then you can use single loop index join. The competing algorithms are hash joins. So you can make use of hash joins and partition hash joins appropriately. So for each of them, for each of these algorithms, you should also have some idea of what is the cost that you are going to pay. So cost estimates. So depending on the kind of indices available, sizes available, the nature of the hash functions, etc., you will have to estimate the, before you actually jump into choose that algorithm, you have to do an estimation of the cost of that using that algorithm and then choose next thing appropriate choice. And this idea of estimation applies to almost all the algorithms that we have to use because then everywhere we have choices of algorithms. Now we can also use this hash based join methods. We can slightly tweak them to actually compute union, intersect and difference also. Union, intersect, union is almost like joins. So basically the join producing algorithms can be slightly tweaked to produce these things. Even the sort merge also can be adapted. So I will not go into the details, please study the details. We will stop here for today. So in the next class I am going to actually talk about, take an example a query and then look at various issues in processing a query. Touch upon what is called query optimization, just give a flavor of query optimization. Okay.